Okay, dear students, last time we were talking about the algebra of operators, and I talked about addition and subtraction of operators. I talked about multiplication of operators. I talked about null operators. I talked about unitary operators. I talked about the commutators. Okay, so and then I left you at this point. What are the commutator operators? And I said you that the two operators A and B, if they give the same value as AB is equal to BA, we say they commute with each other, and if it does not gives the same value, means then we say they do not commute with each other. If you look at the operator X, which is an operator for position, and if you look at the operator of position, and if you look at minus IH cross ddx, that is of momentum, then you will find that x, which we say px, xpx is not equal to px into x. So, we say these two position and momentum operators do not commute with each other. And I said you when I was doing Heidelberg uncertainty principle that any two operators, if they do not commute with each other, then such operators, such functions or such physical variables are called conjugate variables. So, we say that position and momentums are conjugate variables. Okay. And such conjugate variables cannot be determined precisely and simultaneously. Okay. So, this you will find out. You just do it x px and find out its value, then you find out px and x, and for that matter you just take a function of psi. So, what you have multiplication by x, and what is this? This is minus IH cross ddx of psi. So, what you write is x minus symbol IH cross ddx of psi, and here what you write? You write px is minus IH cross ddx into x into psi. So, now you have to differentiate ddx into x and psi on two functions. Okay. So, this will not give you the same value as the previous one. You do it yourself and you will find that x px is not equal to px into x. So, that's how we find out the commutators of two operators. Okay. Now, another property of operators in quantum mechanics is that operators in quantum mechanics are linear operators. What does it mean? It means that if you operate with an operator on a function fx and then you operate with the same operator on a function gx, and if you operate with the operator on the sum of these two functions, and if you get the result same, if you get the equal result, then we say operator A is a linear operator. So, if this relation is obeyed, we say operator A is a linear operator. Okay. For example, reverse of this, take the example of operating with an operator under root, then you operate with the operator on this one, and then you operate with the same operator on the sum of these two functions. What do you see? You see here you get 5 and here you get 7. Both are not equal. So it means under root is not a linear operator. All quantum mechanical operators, position, momentum, energy, angular momentum, all are linear operators. All operators are linear operators. Okay. So linear operators are x d dx d square by dx square. This you get in the momentum operator, this you get in the kinetic energy operator, this is position operator. So all these are examples of linear operator. Linear operator. So in algebra of operators, we talked about what is addition and subtraction of the operators, what is multiplication of the operators, what is a square of the operators, what does that square of the operator means, what is, how does the associative law of multiplication is followed by the operators. Okay. Then I talked about what is the commutator of an operator, and then I talked about what is the linear operator. Another important property of quantum mechanical operator is that they are Hermitian operators. Let us see what is this Hermitian operator. We can define Hermitian operator. If I write an integral for the operator, then we have three terms here: first term, second term, and third term. Third term is complex conjugate. What you do is that you write the integral and interchange the position of first and third. Okay. Sorry. Hermitian operators are first, second, and third term. So what you do is that you interchange the position of first and third. Third you bring here, first you bring here, and then you take the conjugate of the operator also, and if you equate it so that you can write this also, A psi star d tau, then this is called Hermitian condition, and any operator A which follows this relationship is called a Hermitian operator. So this is called Hermitian condition. Hermitian condition. Any operator A is a Hermitian operator. Okay. all operators in quantum mechanics, which you will find in your book, all operators which is used in quantum mechanics is a Hermitian operator. Means all operators I mean position, momentum, kinetic energy, total energy, all operators, corresponding operator are Hermitian operator. Okay. So if you are given an operator and somebody asks whether it is a Hermitian operator or not, you just compare it with the operators which you have seen in your book, in quantum chemistry book. If it is exactly the same, position operator, momentum operator, energy operator, you need to do nothing. Blindly you can say that these are Hermitian operators, but there is a way out to check also. Okay. So what is the way out? What is this Hermitian operator characteristics and how one can check the operators whether it is a Hermitian operator or not. In this case, for finding out the Hermitian operator, what is important is knowing the adjoints. Okay. So for finding out the Hermitian property of an operator, you need to know about the adjoints. So those from mathematics must have done it. Adjoints. Okay. If I write a matrix then you have row 1, row 2. If you write this row 1 as column and row 2 is the second column, then we say this is AT, transpose of a matrix. And if you take conjugate of this transpose, how do you write conjugate? You know you change the sign of I. So it will be 2 minus I and 0. Here you do not have any I, it is 2, so it will remain as such. Here you have I, so it will be minus I, and here you have minus I, so it will become I, and this is transpose of matrix. This is called adjoint. So adjoint is the conjugate of transpose of a matrix. That I think you have done in your BSc level mathematics. Okay, so that you can easily write. So for example, you have a anything else? Okay, then you can again write the B transpose is equal to what? First row, then second row, and then you can write this will be B transpose, B transpose, and then you can write the conjugate of this minus I. So for that matter, any matrix you write, C, it's a matrix, so don't give the symbol of this one, it's B. Let me remove this also, it's B transpose. Okay. Then you have a matrix like 4 into I and 3 minus I. So find out the transpose and it will be 4 I 3 I. You change the row and the column and then you take the conjugate. Conjugate will be 4 3 and it will be minus I and 4 3 I minus I. So it will be minus I and this will be I. Okay. So this way this is your again adjoint. We can apply this concept to the operator system in quantum mechanics. This adjoint of an operator, we can write it if we write operator, its transpose and taking a symbol of conjugate. Then we give a new symbol to this one, dagger, and this is called dagger operator. Okay. And this if you understand this dagger operator, then it is very easy to find out whether a given operator is Hermitian or not. Okay, let's see how to do it. So what we say that if a dagger of an operator is equal to A, we say it is a Hermitian operator. If a dagger is not equal to a dagger, it is not T, it is dagger is not equal to A, or a dagger is not equal to minus A, then it is called non-Hermitian operator. Non-Hermitian operator. And if a dagger is equal to minus A, then it is called anti-Hermitian operator. So this you will have to remember. A dagger is equal to A, it's a Hermitian operator. A dagger is equal to minus A, it's an anti-Hermitian operator. And if a dagger is not equal to A also and not equal to minus A also, then it's called non-Hermitian operator. So this is the definition of a Hermitian operator in terms of dagger operator. And I said you what is Hermitian operator? You will have to remember this, that if you write this integral, then you have three terms, first, second and third, and if you replace the position of first and third and then take the conjugate of the operator, then you say any operator A which obeys this relationship is called Hermitian operator. Okay. Now in terms of dagger operator, we have certain rules which you will have to remember. Okay. So let me write those rules. Rules of dagger operator. General rule. And these rules are a dagger and dagger of a dagger is equal to A. First rule. If you take the dagger of a dagger, that's equal to A. If you take AB dagger, then it is equal to A dagger multiplied by B dagger. B multiplied by B dagger. Okay. So AB dagger is, third is A plus minus b dagger is equal to a dagger plus minus b dagger. Exactly, we are doing the same thing which we did in operator algebra. Okay. Then you have a constant multiplied by a, and if you take the dagger of this one, then it is a star means conjugate of a, and then you take a dagger. Okay. Sorry. Then you have a raised to the power n dagger is equal to a dagger raised to the power n. Then you have dagger of ddx is equal to minus ddx, and then you have dagger of x is equal to x. Okay. So these are the 7 rules of dagger operators, which you will have to remember. And using these 7 rules of dagger operator, you can find out whether a particular kind of particular operator, given operator, is Hermitian operator or not. Say for example, if you have a raised to the power n, and if you have to find out the dagger of this one, then what you write? You write a dagger, a dagger, a dagger, and so on, and so on. N times you write the dagger. N times you write the dagger. Okay. So we will try to find out, we will see some examples that how to proceed with this one. Let's look at the easiest operators which we have, px operator, and find out the dagger of a px operator. Sorry. Dagger of a px operator. And how will you do this? What is px operator? That you know, px operator is minus I h cross ddx. Okay. So if you have to find out the dagger of this one, px, let me write it like px is equal to this one. So if you have to find out px dagger, then how will you proceed? You will proceed like this one, that you will take minus I h cross ddx of dagger. So it will be minus I h cross, you will take the conjugate of this one and ddx dagger, and ddx dagger is minus ddx. So this will be minus I will become I h cross conjugate of this one, and this will be minus ddx. So it will be minus I h cross ddx. So let's see, px was this one and px dagger is this one. What does it mean? Px is equal to px dagger. Sorry. Px dagger. So if you have px is equal to px dagger, it means px is a Hermitian operator. If I give you another example, say I h cross d square by dx square. If you have to find out about this operator, whether it is Hermitian or not, whether it is Hermitian or not. So what you need to find out? You need to find out I h cross d square by dx square, dagger you have to find out. Okay. Sorry, I h cross, it's I h cross only, it's not a square. I h cross I h cross d square by dx square into dagger. So what you write? You write I h cross and then you have ddx into ddx and dagger of this one. So it will be I h cross conjugate of this one and then you take ddx dagger and ddx dagger. Okay, and this is minus ddx, this is also minus ddx, that the rule tells you. Okay, so you have plus ddx. This will be I h cross will be minus I h. Okay, so it will be, this will be plus and this will be minus. So what does it tells you? If I write this as a B operator, then B dagger is actually this one. And if you look at this function and this function, you have a negative sign here. It means what? B is not equal to B dagger, it is minus B. B dagger is, B is not equal to, let me write it like this one, B dagger is equal to minus of B, okay, or B is equal to minus of B dagger, anything you can write, okay. So what is it? It is an anti-Hermitian operator. Okay. So this way we can find out that whether a particular given operator is Hermitian operator or not by using the concept of dagger operators. Okay. A few more examples. If I say ddx is also an operator, ddx is also an operator. So if somebody asks you whether ddx is a Hermitian operator or not, whether ddx is a Hermitian operator or not, that's very easy. ddx dagger you have to find out. And what it will be? It will be minus ddx. Okay, so we say it is an anti-Hermitian operator. Anti-Hermitian operator. If I say whether I ddx, what about I ddx? So what about I ddx? I take the complex conjugate of this one and take the dagger of this one. Okay, so it will be minus I and ddx will be, ddx dagger will be minus ddx, so it will be minus minus plus and I ddx. So you see I ddx and dagger of I ddx, is equal to same. So we say I ddx is equal to dagger of I ddx, and we say therefore I ddx is a Hermitian operator. Okay. So this way you can find out about any operators whether it is a Hermitian operator or not using the concept of dagger operator. So today we talked about that in quantum mechanics the operators which you have, whether they commute with each other or not, two operators, and what is the conjugate variables. In this class we talked about, and then we talked about that what are the property of an operators, what is the linear property, what are linear operators and what are Hermitian operators. And remember this always, that in quantum mechanics all operators in quantum mechanics are linear Hermitian operators. All operators of quantum mechanics are linear Hermitian operator. One of the properties of Hermitian operator is that if you operate with a Hermitian operator on a function, on a function, then you always get a real eigenvalue of the physical variables. This and other properties of Hermitian operators we will do in the next class. Thank you.